everyone, welcome to the channel Statistica. So in previous lecture we have covered the concept of rank and nullity on linear mapping. Now we'll see that how the operations and compositions with linear mappings be defined. Okay, so let's just see that operations with linear mapping. Okay, so for that let's just consider that I have mapping T which is on V to U and another mapping V G which is also on V to U, and these mappings are linear over the field K. Okay, then the operations of this matrix, let's just consider first operations of addition. Okay, then the addition of this mapping which is T plus G of V is equals to T of V plus G of V. Similarly, the scalar multiple of that is KT of V is equals to K of TV. Okay, and these mappings are also linear. Okay, now I am saying that when I have U and V are my vector spaces over the field K. Okay, then the collection of all linear mappings from V into U with the operation of addition addition and scalar multiplication forms a vector space over the field K. Okay, so what I'm saying that I have V and U be my vector spaces which are over the field K, then the collection of all linear mapping which are defined on V to U, okay, with the operation of addition and scalar multiplication, with the operation of scalar and addition and scalar multiplication forms the vector spaces over the field K. And the vector spaces of these linear mappings is denoted by vector spaces of these linear mappings is denoted by homomorphism of V, U. Okay, why am I denoting it by homomorphism V, U? Because homomorphism. What is homomorphism? Homomorphism is basically a map that preserves the algebraic structure. A map that preserves the algebraic structure. By this, I mean to say that let's say if I have a map which is H V to W, and a map that preserves the algebraic structure, which means that let's say I have A comma B which belongs to R and U comma V with the vector spaces. Okay, with the vectors. These are my vectors. Then H of AU plus BV equals to A of HU plus B of HV. Okay. Then we can say a map which can be like this. Then we can say that it is my homomorphism. Where the operation of addition and scalar multiplication are defined. Okay. And here is the case that I have taken the map of all linear mappings with the operation of addition and scalar multiplication. That's why I'm defining these vector spaces by homomorphism of V, U. Now, this homomorphism V, U is my corresponding vector space. That means it satisfies all the 8 axioms of the vector space. Okay. Now, if we look to the dimension of this vector space, what would be the dimension of this vector space? My mapping here for the homomorphism V, U is actually TV to U. And let's just consider that the dimension of V is equals to N and dimension of U is equals to M. Then the dimension of this vector space homomorphism V, U is equals to Mn. Now we'll see that how the compositions of the mappings be defined. Let's see compositions of linear mappings. Whether the compositions of the linear mappings are linear or not. We'll just check that. So for that, let's just consider mapping which is TV to U and another mapping which is G and which is defined on U to W. And these are linear mappings. over the field K. Okay, now the mapping which is V to U and U to W. V to U is defined on the T and U to W is defined on G mapping. Okay, now if I composite this mapping, the composition which is GOT, my respective composition be defined on V to W. V to W is GOT. Okay, which is defined as GOT of V is equals to G of TV. G of TV. I am applying G on the T mapping. Okay, so let's just fact check that. For that, let's just consider that for any u v comma w, for any v comma w which belongs to the vector space v, and a comma b with a scalar which belong to the field of scalars, let's say k, then got of av plus bw is actually equals to g of t of av plus bw. Okay, which can also be written as g of a t of v plus b t of w, which is equals to a g of tv plus b g of tw. Okay, and this can be written as a got of v plus b got of w, and you can see that this is linear. So from this I got that my got is linear. Got is linear. Okay, so what did we get? That if we have mapping T which is on V to U and another mapping G which is on U to W, then V to W is my corresponding composition which is GOT, and that mapping is also linear. That mapping is also linear. That composite mapping is also linear. Okay. Now if I have the mapping which is as T V to V, that is a linear mapping from V to itself. Okay, and these type of mappings are called linear operator, linear operator, or you can also say linear transformation on V. Okay, now these types of mapping can also be denoted as homomorphism of V comma V. This homomorphism of V comma V can also be written as A on V, a on V, and this is corresponding vector spaces as homomorphism v comma u. V comma V is my corresponding vector space, so I am denoting the here homomorphism on v comma V by av. So av is my vector space over the field k. I am defining this mapping like this. Okay, over the field k, then what will be the dimension of this av? The dimension of this av will be equals to, let's just consider that the dimension of v is equals to n, and as the mapping is from v to v, then it will be n into n, which is equals to n square. Okay, this will be the dimension of this vector when the mapping is going from v to itself. Okay, now we'll see that what will be the case in the square matrices. That square matrices as linear operators, as linear operators. Okay, now let's just consider that M is my vector space of all n cross n matrices, of all n cross n matrices. Okay, and I have a matrix A n cross n which is on the transformation case power n to case power n, which is V to V. Okay, on the same vector space. Okay, so as it is going from same vector space, I can define it as linear operator. Linear operator, and how the matrix mapping is defined, which is PAU equals to AU. Okay, now for that, let's just consider two mappings A comma B. These are my two matrices actually, two matrices which are from the M vector space of all matrices. Okay, now the matrix product AB, the matrix product AB, let's just for any vector, matrix product AB for any vector, for any vector u in this, in the vector space case power n is defined as, okay, so for tabu, TAB for the vector u. How this matrix product of this mapping be defined? TABU is equals to, by this we can write it as ABU, okay, which can be written as A of BU. Okay, and now I can write this A of BU equals to A of BU can be written as TBU. Okay, by applying this. Okay, similarly, I can write this A of TBU equals to TA of TBU. Okay, and which can be written as TAO TBU by applying the composition. So, and similarly for the product, sorry, the addition of the matrices, if I add two matrices, what will be the case then? That A plus B of V is, U is equal to AV plus BV, and I can write that, sorry, AU plus BU, and I can write that TAU plus TBU, and that can be written as TA plus TB. Okay, so from this we can see that the matrix product and the matrix addition corresponds to the composition of A and B as linear mappings. Okay, that from this we got that matrix product of the matrices and sum of the matrices, also composed to corresponds to, you can write composed to linear mappings. They also form linear mappings. Okay, why am I defining all this? Because we are going to use that if I'm applying the product, if I'm taking the product of the two matrices, for that I have to check first whether the product of the two matrices is linear mapping or not. So we are just checking that I have, let's say, two matrices, then the matrix product of the matrices are also linear mapping, and the addition of the two matrices are also linear mapping. Okay, so at that time we'll not have to check that whether these are forming linear mappings or not. Okay, now we'll see a very important concept, which is our matrix representation representation of linear mapping. Okay, matrix representation of linear mapping. So for that, let's just first consider the case of my mapping which is on TV to V. Okay, for linear operator when my vector space is going to itself, which is V to V. Okay, so for that, this is my corresponding linear operator, and S is equals to U1, U2, UN. These are the corresponding bases of this vector space V. Okay, these are the corresponding basis vectors of this vector space V. Okay, and what will be the images of this vector space? That TU1, TU2 to TUN. These are the vectors in V, because mapping is going from V to V. So the images of these vectors will also belongs to this vector space V. So from this we can see that I can write these images in the linear combinations of these basis vectors, because the mapping is going from V to V, from the same vector spaces to same V to V. Okay, so I can write this image vector V of V1 in the linear combinations of this basis vector. For the scalars AIs, let's just consider that. Let's just write them in the linear combination. So T of V1 can be written as A11 U1 plus A12 U2 to A1N UN. Okay, and for the second image, T of V2 can be written as A21 U1 plus A22 U2 to A2N UN. Okay, similarly for T of Vn, this can be written as AN1 U1 plus AN2 U2 to ANN UN. Okay, now The transpose of above coefficient, the matrix of coefficient. What are the matrix of coefficient? The matrix of coefficients here are a11, a12 to a1n. Okay, coefficients of this matrix, which is a21, a22 to a2n, and similarly an1, an2, ann. This is the matrix of coefficient. Okay, now the transpose of this matrix. Why are we taking the transpose? Because we have studied earlier that the the corresponding coefficients of the image vector are the image of t is r forms the is equals to the column space, r equals to the column space of the matrix. Okay, so we are not writing the coefficients of this vector into the row form. We'll take transpose of this matrix. We'll write these vectors in the column form. It's like this: a11, we'll write this vector, the coefficients of the vectors as a11, a12 in the column form, which is as like this. And similarly for tv2, a21, a22 to a2n, and an1, an2 to ann, which is the matrix represents. So this is our corresponding matrix representation of T relative to basis S. Okay, using column coordinate vector notation. We are taking these vectors in the column coordinates. Okay, now you can see that this matrix. Let's say this is the matrix M. This matrix M is actually, this is how we can denote the column vectors. Okay, by this uh, okay, this is how we can define the column vectors. So the column vectors relative to the basis S. Now I can write this matrix S in the column vectors like this, that T of u1 on the basis S, similarly T of u2 on the basis S, and T of un on the basis S. And these are my corresponding columns of the matrices with the coordinates of TU1, TU2, TUN. I am taking A11, A12, A1n in the column format, because the image space of T, that this is the corresponding image of this basis vector. The image space of T is the column space of the matrix. It is the column space of the matrix. That's why I am saying that if I take the transpose of the matrix, if I take the transpose of this coefficient of the matrix, I can write this in this whole x, let's say star, in the matrix format like this. That's how we can write this. Now if I take the transpose of that matrix, I get my corresponding matrix representation of T relative to my basis S. Okay, now let's just see that how can we actually define it. Okay, let's take an example. How can we use that? So let's say my mapping is going from r square to r square. Okay, and my mapping is tx defined as tx comma y equals to 2x plus 3y comma 4x minus 5y. Okay, now I want to find the matrix representation of t relative to basis S, where S is equals to u1, u2, and u1 is 1 comma 2 and 2 comma 5. Okay, so what have I done earlier? So for that, what are we doing here? That I have given the basis vector. Now we'll first find the images of these vectors. Okay, so let's just find the images of these vectors. That T of u1. What would be the T of u1? That is T of 1 comma 2. T of 1 comma 2 equals to, if I'll put the 1 comma 2 in this, I'll got 2 into 3 into 6, which is 8, and minus 6. Okay, and T of u2 is equals to T of 2 comma 5, which is equals to hmm, uh, let's just put it here, 2 to 4, 5 to 15, and it will be 19, and this will be 4 to 8, 5 to 25, it will be minus 17. Okay, So these are my corresponding images of my basis vector. Now I have to, as the field is going, as the vector space is going from R square to R square, I can, my corresponding images will also belong to this, T of u1 will also belongs to this field vector space R square. So I can write these vectors of T u1 in the linear combinations in my basis vectors. Okay, as they are on the same vector spaces. Okay, so now T of u1 can be written in the linear combinations of the basis vector, which is equals to T of u1 equals to 8 comma minus 6 equals to, in the linear combination of this, let's consider x comma 1 comma 2 plus y 2 comma 5. I am writing this like this, but these are my corresponding actually the column vectors. Okay, these are my corresponding column vectors. So 8 comma minus 6 equals to, uh, okay, let's just solve that. That 8 equals to x plus 2y, and second equation I got that minus 6 equals to 2x plus 5y. Let's just solve these. From this I got 8 to the 16, and 2x plus 4y, which is minus, change the signs. From this I got that y equals to minus 22. Okay, and by putting y here I got x equals to 52. Okay, so from this I got that tu1 can be written in the linear combination of the column of the basis vectors as 52u1 minus 22u2. Similarly, we'll proceed for the u2 basis vector, which is tu2 equals to 19 minus 17. I can write this 19 comma minus 17 like x comma 1 comma 2 plus y comma 2 comma 5. From this I got the equations as x plus 2y equals to 19 and 2x plus 5y equals to minus 17. Okay, let's just multiply this equation by 2, and from this I got 2x plus 4y equals to 38 and 2x plus 5y equals to minus 17. Okay, let's just change the signs, and from this I got minus of y equals to 55. Yes, it is 55. So y equals to minus 55 and x equals to 19 minus 55, which is 110. Okay, so y equals to 19 plus हो जाएगा actually. Sorry, x equals to 129. Okay, so I can write this tu2 in the linear combination of basis vectors as 129u1 minus 55u2. Okay, so this is my first representation and this is my second representation. Okay, now I can write them in the matrix format as t. I am writing this because this is representing the matrix T on the correspond with the corresponds to the basis vector S, corresponds to the basis S. Okay, I can write this in the matrix format as we have seen that the corresponding coordinates of the image vector are actually the columns of the matrix. So we'll represent the coordinates of this matrix, of this image vector into the columns of the matrix, which is 52 minus 22, and for that it is 129 and minus 55. Okay, okay. Now let's just see by matrix mapping how the matrix mapping and the matrix representation be performed. Okay, matrix mapping and matrix representation. Matrix representation. How can we find the matrix representation of the transformation on the matrix mapping? Okay, so let's just consider A is my corresponding matrix with the elements as A 4 minus 3 4 minus 2 minus 5. Okay, this is my linear operator, which is the matrix is going from R square to R square. Okay, and the corresponding bases of this matrix are U1 U2. Okay, and which are actually 1 2 and 2 5. These are my bases of R square. What? These are bases of R square. Okay, how the matrix mapping is defined? We know that the matrix mapping is defined as TAU equals to AU. Okay, so we'll use that here. So if I want to find the image of the u1 vector, then I'll apply T of u1 equals to Ta of u1 is actually au1. Okay, we'll multiply this by, let's just take the basis vector as standard basis, which is 1 0 0 1. Okay, the process will be similar that if we'll have to apply for the another basis, but I have to show some result actually, that's why I'm taking for the standard basis. Okay, let's just take for that. So au1 if I multiply this matrix A by my corresponding u1 vector, which is 1 0, what will I get? I got 3 4. Okay, and similarly for Ta of u2, I'll got A into u2, which is I'm multiplying matrix A by u2, which is 0 1. Then I'll got minus 2 minus 5. Okay, now I have to represent this Ta u1 in the linear combinations of this basis vector. So this Ta u1, which is 3 4, can be written in the linear combinations of these basis vectors as 3e1 plus 4e2, because these are our standard bases. Okay, and similarly minus 2 minus 5 can be written in the linear combination as minus 2e1 minus 5e2. Okay, so we got our matrix as by, if we'll, I'll just transform the coordinates in the column frame form, which is 3 4, and similarly for this, which is minus 2 minus 5, which is equals to our original matrix A. You can see that. Okay, this is our this is equals to our corresponding original matrix A. So the result here is that the matrix representation, that the matrix representation of any n cross n square matrix, any n cross n square matrix A over the field K relative to usual basis. Usual basis, by usual basis I mean on the standard basis, which are e1 e2 e3. These are my corresponding usual basis. Okay, so usual basis E, let's just consider E of k's power n is the matrix A itself. That is that AE equals to A. Okay, I mean here that the matrix representation of any square matrix, I am taking any square matrix, here it is 2 cross 2 over the field K. Okay, and over the, this is my corresponding basis, and I am taking the matrix representation on the standard basis. If I'm taking the matrix representation on the standard basis, then the matrix representation is the original matrix itself. Okay, and if the bases are not the standard basis, then the matrix representation of the matrix mapping is different, then it will be anything. Okay, so that's the result that I want to show, that's why I have taken the standard basis here. Okay, now let's just see a very important example, which is t r square to r square. This is my corresponding mapping. Okay, now if I say that the mapping t is rotation in r square counterclockwise counterclockwise by 90 degree, by 90 degree. Okay, and from that I have to find the matrix relative to our usual basis, that is relative to our standard basis. Okay, now this is given. Okay, so we have studied the transformation of rotation, let's say maybe the 10th lecture, I didn't remember that, but we have covered the concept of rotation. Okay, so if we'll perform the rotation, then I got the rotation matrix. If you didn't remember the rotation matrix, then you will not able to do this question. Okay, so it is important to remember, or remember the some matrices which are rotation matrices and reflection projection. These are some examples that are very important and which are asked very frequently. Okay, so my corresponding rotation matrix, if you'll remember from our previous lecture, is actually cos theta minus sin theta and cos theta. This is my rotation matrix. Okay, rotation matrix in the counterclockwise direction. Okay, we have performed this example. So in the counterclockwise direction, this is my corresponding rotation matrix. So if I perform the transformation, which is mapping, which is PV, which is equals to AV. Okay, this is my corresponding linear matrix mapping, which is TAV equals to AV. So I'll perform similarly for that cos theta minus sine theta cos theta into V. Okay, and T is rotation in R square counterclockwise by 90 degree. That my theta is actually 90 degree. So I'll just put the values that 90 degree, 90 degree, 90 degree and 90 degree. Okay, and what is the value of cos 90? Cos 90 is 0 and sin 90 is minus and it 1 actually, and it will be minus 1, and sin 90 is 1, cos 90 is 0. So this is I got. Okay, this is my matrix A. This is my matrix A in the counterclockwise direction by 90 degree. And I want to find the matrix relative to the standard basis. Okay, relative to the standard basis. So if this is my AB. Okay, so my standard bases are actually 1001, 10001, and in the previous theorem, this is theorem which in this we have studied that the matrix representation, this is my n cross n, this is also n cross n, which is 2 cross 2 matrices. So in the matrix representation of any n cross n square matrix over the field K, to the standard basis to the usual basis is the matrix itself. Okay, and we have S as our standard basis. So the corresponding matrix representation for this will be my matrix A, which is equal to cos theta minus sin theta, 0 minus 1 1 0. This is my matrix representation relative to standard basis. Okay, so you can also check that by performing like this, as I have done in this example. You can check that. Okay, now let's say that my mapping is T R square to R square, but T is defined actually by the reflection. Okay, T is defined and reflection in R square by line y equals to minus x. Okay, and I have to find the matrix representation under the usual basis. Okay, let's just find on the standard basis. Okay, but the mapping is defined on the reflection in R square by the line y equals to minus x. And for that, what will be my matrix representation? Okay, so let's just find the standard basis. What will be the standard basis? Standard basis are actually 1 0 and 0 1. Let's just find the images of this. What will be the image of t1 comma 0? And what will be the image of t of 0 comma 1? Okay, so you can see that the image of t of 1 comma 0 is actually 0 comma minus 1. Okay, so let's see it like this, that x is, this is y. Okay, that 1 0 1 0, this is 0, this is 1. Okay, sorry, this is 1, this is 1. So this is my 1 comma 0 and this is my 0 comma 1. 1 0 comma 1 and this is 0 1 0. Okay, and the line is y equals to minus x, y equals to minus x. So I just, if I reflect the point 1 comma 0, okay, by the line y equals to minus x, what will be, what will I get? I got 0 comma minus 1. Okay, and similarly for t of 0 comma 1, I'll got minus 1 comma 0. Okay, this is my point 0 comma 1 and this is my point 1 comma 0. And what is the line y equals to minus x? The line y equals to minus x goes like this. Okay, this is my y equals to minus x. And if you see the reflection of this point on this line, if you see the reflection of this point on this line, it will lie here, which is my point 0 comma minus 1. Okay, and if you see the projection reflection of this point, which will be like reflection of this point, which will be like there, here it will be here, which is what is this? This is minus 1 comma 0. This is point this. Okay, on the line y equals to minus x, this is the corresponding reflections of these lines. Okay, so the image of point 1 comma 0 by line y equals to minus x equals to 0 comma minus 1, and similarly for 0 comma 1 it is equals to minus 1 comma 0. Okay, as these are on the standard basis, so the corresponding vectors, that is 0, minus 1 and minus 1, 0, are the matrix representations for this standard basis, corresponding to the standard basis. Okay, so we have done this in the counterclockwise and the reflection. Similarly you can do for the projection form. Okay, because these are very important. Just remember these, that if you didn't remember this matrix, then it will be a problem. Just there are some examples which are important actually for the, let's say, rotations, reflections, projections. These are important. You have to do these examples in the linear mappings when you study the matrix representation. Okay, now let's just consider mapping which is as r cube to r square. Okay, t r cube to r square. This is my mapping. Okay, and alpha 1, alpha 2 to alpha 3, alpha 1, alpha 2, alpha 3, and second beta 1, beta 2. These are the ordered bases of the real vectors v and w. Okay, as the matrix is going from v to w. Okay, you can also write it like this. Okay, the matrix is going from v to w, and these are the corresponding order bases of this matrix, and where the mapping is defined as the t of alpha 1 equals to beta 1 plus beta 2, and t of alpha 2 equals to 3 beta 1 minus beta 2, and t of alpha 3 equals to beta 1 plus 3 beta 2. Okay, now I want to find the matrix T relative to the ordered basis. Okay, find matrix T relative to ordered basis. First, take it as alpha 1, alpha 2, alpha 3 of V and beta 1, beta 2 of W. Okay, because this is not linear operator. Here it is not a linear operator, as the vector is going, as the matrix is, as mapping is going from V to W. Okay, and second I have to find the matrix related to the basis alpha 1 plus alpha 2 comma alpha 2 alpha 3 of V, and beta 1, beta 2, beta 3, beta 1 plus beta 2 of W. Now I want to find the matrix T represented with respect to these. Okay, let's just find for first. So from first you can see that alpha 1, alpha 2, alpha 3 of B and beta 1, beta 2 of W. That's how we have defined the linear mapping here. That the corresponding linear mapping of alpha 1, alpha 2 and alpha 3. The corresponding images of these ordered bases are this, which are in the form of beta 1, beta 2, beta 1, beta 2 in all these cases. So I can simply write the matrix which is like, let's say T. Okay, I can simply write this vector if I form these corresponding coordinates of these images vector in the column format, which is 1, 1 and 3 minus 1, 1, 3. These are my corresponding matrix representation relative to these order bases. Okay, and my main point of concern for the second, which is if I want to find the matrix representation with these basis vectors, which is for that I have to find the images for alpha 1 plus alpha 2 and alpha 2, t of alpha 2 and t of alpha 3 of V. Okay, in the terms of beta 1 comma beta 1 plus beta 2 of W. Okay, so let's just find that t of alpha 1 plus alpha 2 is actually t of alpha 1 plus t of alpha 2, which is equals to beta 1 plus beta 2 plus 3 beta 1 minus beta 2. And that will be equals to, if I sum these two, and that will be equals to, I think, 4 beta 1, 4 beta 1 plus, I can, in the terms of this is 4 beta 1 plus 0 of beta 1 plus beta 2. Okay, and t of alpha 2, which is equals to 3 beta 1 minus beta 2, and in the terms beta 1 and beta 1 plus beta 2, I can write it as 4 beta 1 minus beta 1 plus beta 2. Okay, similarly of t of alpha 3, which is beta 1 plus 3 beta 2, I can write it as minus 2 of beta 1 plus 3 beta 1 plus beta 2. Okay, I have just, this is beta 1. Okay, So I have written all these images vectors of alpha 1 plus alpha 2, alpha 3 because I have asked in corresponding to these vectors. Okay, I have taken the images of these vectors in the terms of beta 1 and beta 1 2 plus beta 1 plus beta 2. Okay, now I can find the matrix representations of this by putting the coefficients of the corresponding images into the column vectors, which is 4, 0, and for that it is 4 minus 1, 4 minus 1, and for that it is minus 2, 3. Okay, so it is important to note that for which vectors we are finding the matrix, that for which ordered basis we are finding the corresponding matrix. Okay, now let's see. If I have the ordered, if I have the mapping which is as TV to EV, okay, and alpha 1, alpha 2, alpha 3, this is my corresponding ordered basis, or you can say basis of P. Okay, and I'm sorry, T of alpha 1 is actually defined as alpha 1, alpha 2 plus alpha 3. T of alpha 2 is equals to alpha 1 plus alpha 2, and T of alpha 3 is equals to alpha 1. Okay, and I want to find the T inverse relative to alpha 1, alpha 2, alpha 3. This is what very important to note, that in which respect we have to find the inverse, and in which respect we have to find the matrix representation. Here we have to find the for T alpha 1, alpha 2, alpha 3. Okay, let's just find for that. So we know that for that, if I can write it as T inverse of alpha 1 plus alpha 2 plus alpha 3 equals to alpha 1. For this, I can write it as P inverse of alpha 1 plus alpha 2 is equals to alpha 2. And for this, it can be written as P inverse of alpha 3 equals to alpha 3. Okay. Sorry, it is alpha 1. It is alpha 1. Okay. So, I got that T inverse of alpha 1. Sorry, it is alpha 1. T inverse of alpha 1 equals to alpha 3. Okay, by this. Okay, and this can be written as T inverse of alpha 1 plus T inverse of alpha 2 equals to alpha 2. So from this I got that T inverse of alpha 2 is equals to alpha 2, and what is my T inverse of alpha 1, which is alpha 3, so alpha 2 minus alpha 3. And similarly, the T inverse of this can be written as T inverse of alpha 1 plus T inverse of alpha 2 plus T inverse of alpha 3, which is equals to alpha 1. Okay, and I can find T inverse of alpha 3, which is equals to alpha 1 minus, just put the values of this. So this will be alpha 1 minus alpha 2 plus alpha 3 minus alpha 3, that is equals to, that they will cancel out alpha 1 minus alpha 2. Okay, so I got corresponding inverses of this image of these vectors, which is alpha 1, alpha 2, alpha 3. Now if I want to find the matrix representations of this T inverse, what will I do? I'll just transform the coefficient of these corresponding T inverse, the images of these alpha 1, alpha 2, alpha 3 T inverse into the column vectors. I am saying that if I want to find, if I say that find the matrix representation of T inverse correspond to the alpha 1, alpha 2, alpha 3, then what will I do? That the matrix of T inverse is actually equal to, if I'll just write the coefficients of these T inverse images into the column vector, which is, for this is it will be equals to 0, 0, 1, and T inverse alpha 2 it will be 0, 1 minus 3, well, 0, 1 minus 1, and for this it will be 1 minus 1, 0. Okay, so this is my corresponding matrix representation of T inverse relative to the basis alpha 1, alpha 2, alpha 3. Okay, so that's how you can represent any matrix. So that's how you can represent matrix representation in the linear mappings for the corresponding basis. Okay, thank you. This is all about matrix representation. That's all for now.